So today we'll start a new topic, that is stereoisomerism. Structural isomerism we have already done, and we have understood the different isomers what can come under it. So in structural isomerism we had spoken about position isomerism, chain isomerism, metamerism, tautomerism, etc. Right now we'll be talking about stereoisomerism. So there are two type of isomerism what we deal with. One is structural and second is stereo. So in structural, the major difference between the isomers was that their molecular formula was same, but their if you look at their structural formula or condensed formula, it was different, as well as their properties were also different. Now, when I'm talking about stereoisomerism, the important thing which you need to understand in stereoisomerism is, so if you take two stereoisomers, their 3D representation would be different. So alignment of different molecules around the carbon which is being noticed, or which we are talking about, will be different from its respective isomer. So your molecular formula will remain same, your structural formula will remain same, only 3D representation will be different. So what do we mean by 3D representation? I'll tell you. For explanation of 3D represent, I'll show you one demonstration. So now if I'm holding my molecule like this is the way how I'm looking at the molecule. Just imagine from my point of view. So this is the group. Yellow color pen is the group which is towards me. Look at this black color pen which is towards you, basically away from me, and these two are at the almost same plane. Red and blue are almost at the same plane. Okay, so 3D arrangement is that yellow is here, black pen is here, red pen is here, and blue pen is here. If a viewer will look at it, this is how he will look. Yellow pen will look like as it just this molecule is towards the viewer. Black will look like as it is away from the viewer, and blue and red both will have the same arrangement, or basically you can say it will be almost in the same plane, right? So this is called 3D arrangement. So if I look at molecule like this, right now for this molecule, yellow is towards me. If I change their respective positions, now what is towards me? Black is towards me and yellow is away from me. Okay, so this kind of arrangement change in a molecule, in three-dimensional molecule or in a three-dimensional representation, this kind of change, which will not bring any kind of molecular formula change, but will bring some changes in terms of chemical properties, this is called stereoisomerism. And this is just one example I have tried representing you, but there can be multiple such examples, and there will be multiple different ways to express the stereoisomerism. So we have to understand what all will be same in the stereoisomers and what will be different in stereoisomers. So your molecular formula will remain same, your structural formula also will remain same, your IUPAC name of the isomers will remain same, and the fourth comes is degree of unsaturation. Degree of unsaturation. So what does degree of unsaturation means? Degree of unsaturation means total number of pi bonds plus total number of rings in a molecule. Total number of rings in the molecule, or you can write it as or the total number of rings in the molecule. So whatever the number of pi bonds are there in a molecule will still remain same. If there are rings in the molecule, that will still remain same. So degree of unsaturation is not going to change. So we have not done much about the degree of unsaturation yet. I'll be doing this as a separate topic. Okay, but for now, just to get a small idea, degree of unsaturation is just representation of number of pi bonds and number of rings in the molecule. So that will also remain same. What will be different? Different will be your stereochemical formula. What is stereochemical formula? A 3D representation of a molecule. That is your stereochemical formula, where we can actually represent which particular molecule attached on a carbon is towards the viewer, and which particular molecule on the carbon attached is away from the viewer, the way how I have shown you it in the molecule. Okay, now let's talk about the stereoisomers. Stereoisomers are also of two types. One is configurational isomer and second is conformational isomer. Configurational isomers are the ones which can be separated. That means their properties are little different. Physical properties like their melting point and boiling point is a little different, or there some chemical properties are different, due to which one may react with something and other isomer of it may not react with something, and that can be a point of difference which you can use to isolate two different isomers from a mixture. So basically you can isolate two isomers if they have been mixed together, or if the whole product which is forming is the mix of two isomers, you can separate them out. Whereas conformational isomers are the ones which have different 3D representation but have no difference in their chemical properties as well as in the physical properties. So there is no point through which you will be able to isolate them. You can just see and you can understand that there are different 3D representations for a molecule, but you cannot separate them out at any point of time. Okay. So configurational isomers are of two types. One is enantiomers and second is diastereomers. What are enantiomers? Enantiomers is nothing else but the mirror image of a molecule. So I have taken, let's say this. This is my hand. Let's assume this is a molecule. Okay, this is my hand, and this is going to be the mirror image of this hand, right? So if I'll watch, if I'll see an image of this palm, this will be the image of this will be the mirror image of the palm. So basically mirror images of a molecule are called as enantiomers. Okay, in enantiomers also two different type of molecules you will get. One is erythro and second is threo. So one is erythro and second is threo. We will do all of these categories in detail. Next is diastereomers. Diastereomers means non-mirror image isomers. So this is my hand, this is a molecule, and this is the another molecule, assume. These two are not mirror images of each other, but isomer of the same molecule. Okay, such kind of molecules or such kind of compounds are called as diastereomers. Now diastereomers also can be of two types. One is geometrical isomers and second is optical diastereomers. So all these categories we will be discussing in detail. The first thing which we will be talking about is geometrical isomers. Okay, so geometrical isomers we will discuss now. This is a small intro about what all different kind of stereoisomers you are going to encounter coming forward. So now we'll discuss about the first isomerism, that is geometrical isomerism. Now to understand geometrical isomerism, you have to understand what are the conditions required for geometrical isomerism and in which all kind of setup it will be shown. Geometrical isomerism is not possible for all type of molecules, only specific type of molecules can show geometrical isomerism. So before I explain you what all different type of groups can do, you need to understand the basic requirement for geometrical isomerism, that is restricted rotation system. That means this isomerism occurs only in those cases where rotation doesn't happen or rotation between one carbon and other carbon bond is restricted. For example, if I talk about carbon-carbon single bond, this bond can always rotate. If you don't know, you have let's write it like this. So if you have carbon structures, if this is your compound, okay, this carbon-carbon bond can always rotate, okay, and this can rotate. Right now it is in this position. If the rotation will happen, if let's say this carbon rotates like this will become, let's say the rotation is happening, this is carbon 1, this is carbon 2, rotation is happening on the second carbon, it may convert into this after some time. So rotation keeps happening in case of carbon single bonds. Okay. Now when you talk about the pi bonds and the cyclic rings, they do not tend to rotate at all. What kind of systems can show the geometrical isomerism? Where you have carbon double bond carbon, not only carbon double bond carbon, generally carbon double bond with any other thing, or many other cases where you have pi bonds, all those can show the geometrical isomers. And the rings also have restricted rotation, they cannot rotate. When they cannot rotate, they will be able to show the geometrical isomerism. So any kind of cyclic ring, N double bond N, C double bond N and C double bond C, in any of the molecule, if any of these conditions are present, they are capable of showing geometrical isomerism if other conditions fulfill. Okay. So you will write the definition of geometrical isomerism right now. Write down GI arises due to the difference in the arrangement of the grouper molecules present in the restricted rotation system. So how the arrangement has been done in a restricted rotation system, that will bring geometrical isomerism in a molecule. Now what this definition means, we'll talk about it now along with the case discussion, that is GI in C double bond C. Okay, so let's take an example. I have C double bond C and I have 4 groups attached to it. Let's say on the carbon, on the first carbon there is a group A attached, and the same A group is attached here also, then B here and then B here. So A be attached on the first carbon and A be attached on the second carbon. Now if I write A, B and B, A like this, is it any different from, is this molecule 1 is different from molecule 2 in terms of naming or molecular formula or structural formula? No, right? And even number of double bonds are also same, so degree of unsaturation is also same. So there is no difference if I look at this molecule first and molecule 2. There is a slight difference. If you see very carefully, I had written A and B here, and here I have written B and A. Arrangement of the molecule is little different, but it should not bring any difference in the molecule as such, according to the structural isomerism. But this molecule 1 and molecule 2 is different with respect to each other. Why it is different? So difference comes due to the energy difference between the molecule 1 and molecule 2. Basically, conversion of 1 to 2 requires some amount of energy, and that energy is not negligible. That energy has some good amount of value, which also helps us in isolate these two molecules with respect to each other. Basically, what we can say, there is a energy barrier. Basically, let's say if one molecule is cis, so let's say this is energy graph, and this is your compound 1 and this is compound 2. So conversion of compound 1 to compound 2 takes some amount of energy. Energy increases, reach to a certain level, there will be a change in the configuration at this point, and then slowly the compound 2 will form. So this energy barrier is a good amount of energy which actually helps us in isolating the molecule. That means it can be difference in the boiling point, it can be difference in the melting point, it can be difference in any of the temperature based thing which will help us in creating difference. If one, assume if let's say if compound 1 has a melting point of let's say 250 Kelvin, assume, I'm just randomly taking something, 250 Kelvin, or let's write boiling point. Boiling point is 250 Kelvin. Then second will have the boiling point of, assume, 275 Kelvin, which is good enough difference to isolate first and second. That means the switch of compound 1 to compound 2 cannot happen automatically. We have to apply certain amount of energy so that compound 1 can convert into compound 2. Otherwise, it will remain compound 1 only. It will not convert automatically. Interconversion is not possible unless you supply some amount of energy. Right? And interconversion could have happened if this bond rotation was possible. The C would have just rotated, and then this B would have come up and A would have come down, but that's not happening here. This is a restricted rotation system. So actually what will happen when first has to convert into second, the bond between carbon and B will break, the bond between carbon and A will break, then the new bond formation, and that bond breakage and new formation of the bond will have this kind of graph. So this will happen in this energy barrier. So this topmost energy will be required for bond breaking, and then when the new bond will start forming, the energy will become lesser, and once the molecule will be formed, once basically the bond between carbon B has broken, the bond between carbon A is broken, now B will go and attach on a different 3D direction, and A will attach on a different 3D direction. When the attachment will start, the energy will again become lower and the molecule will have lesser energy overall. So this is first, this is second. I have shown the graph over here, so I'll just rewrite it here. What is happening? I had the compound 1 over here. At this energy, the bond between A and B of the first is broken. Now A is individual and B is individual entities, and carbon has two unfulfilled valencies, A and B. Now this B will go and attach at this site, and A will attach at this site, and then the energy graph will go low. That means when the attachment will happen, the energy will become lesser, and when the compound will form completely, it will become A, B, double bond, B, A, then it will become the compound second. So high amount of energy is required for this conversion. That means the bonds will completely break and new bonds will form. That is why this is called a restricted rotation system. These are the two isomers of each other, and that is why these are isolable also. because they are not interconvertible on their own. It requires some amount of energy. So there is energy difference between the molecule 1 and molecule 2. Is this part clear? Now we'll talk about the conditions what are required in geometrical isomerism of C double bond C. So conditions for GI in carbon double bond carbon setup are, first is we have got to know, and now it is true for other compounds also, that we require a restricted rotation system. In carbon double bond carbon, the restricted rotation system is nothing else but the double bond. So it is mandatory that double bond presence should be there in the molecule. Second important condition is, just look at it. If I have C double bond C, I have A, I have B, I have A and I have B. Now when the relative positioning changed, now it became A, B, B and A. So position changed from this to this, right? I could identify the change in position only when there were different set of groups present between the first carbon and the second carbon, right? Basically, individually the carbon double bond carbon should have two different type of groups present. If it would be A over here, okay, then this would be the setup. Just understand, if I would have two A's over here and AB over here, again two A's over here, then it would have shifted to BA. Still, see here, the whole point is the two A's are facing each other. So basically two A's are at the same plane. Okay, so these two A's or these two A's are on the same plane is no different. Again, I'll explain you what was the difference between this setup and this setup in a 3D geometry. In 3D geometry, these two A's were in the same plane, same side basically, and these two B's were in the same side in a 3D, in the 3D geometry. So it's like this. Let me just show you. So I'll tell you this, I'll explain you this through a demonstration. Now assume this is my book. This book is the carbon double bond carbon. So here is one carbon, here is the another carbon, and there is a double bond in between. If you look at the system is continuous and cannot be broken or rotated through any way. Okay, so the chance of carbon rotating and changing its configuration is quite not possible. I have two blue pens here which I can mark it as A, and two red pens here which I can mark it as B. Okay, so now if I put it like this, or if I rotate it like this, I have not broken any bond, to be honest. What I have done, I have just simply rotated the whole molecule. I have not rotated it through a bond or anything. Just molecule has got, it's like this. This is how the molecule just moved like this. That's all. No carbon double bond carbon has been moved. So no matter two red pens are in the front, or two red pens are like this and blue pens are like this, or it's the other way around like this. Like this, the molecule still remains the same. Molecule is not different, and neither it is two different isomers. But if I switch over the position of red and blue, bring the blue over here and put the red over here, I have actually broken the bonds and adjusted the arrangement of A and B. Now this is different. Now blue and red of this are in one plane, and blue and red of this side are in one plane. A is diagonally opposite to another A, and B is diagonally opposite to another B. So basically, if I have to write it on the board, C double bond C A, B, B is equivalent to C double bond B, B, A and A. Here this and this molecule is nothing else but the same thing. The complete rotation of the molecule has happened and this become this. But if I compare it with C double bond C, A, B, B, A, then it is different. In this case, so A and A were in the same plane, B and B were in the same plane. Now A and A are opposite to each other, and B and B are opposite to each other. Such things are, anyways, I'll just tell you the name. This is called as cis. The ones who are, which are when the groups are in the same plane facing same area, that is called as cis, and where the same groups are opposite to each other, those are called as trans. Okay, so we are not getting into cis and trans by the way. I'm just telling you the exact picture of the system. You will be able to see the change only when you have different molecules attached on the individual carbon. Then only you will be able to identify whether the group has changed its position or not. If it would be C double bond C, A and B. Now in this case these two groups are anyways same, right? Now if it is even switched, let's say if the B and A's position is switched, it is still the same molecule. You just rotate the molecule and it will become this. There is no difference between this molecule and this molecule. You just do a complete rotation and it will become this. So in such kind of setups, there is no geometrical isomerism because you rotate the molecule and get the same molecule. GI is only possible in those systems where the individual carbon containing double bond have two different groups attached to them. I hope you have understood. I tried showing it through the demonstration. If you're still not clear about it, you can ask me over the phone or you can ask me on the WhatsApp. But the only thing which you have to remember is two groups should be facing each other. Those two groups which are facing each other, no matter I have written them up or I have written them down, they are basically the same content. They are basically called as cis. Now if I'm just reiterating, if C double bond AA is written over here or AA written over here, it won't make any difference in the molecule. Molecule will still remain the same. Okay, because this is just the rotation of this molecule. This molecule, if it is rotated completely, it will become this. I'm talking about, again notice, I'm talking about the molecule rotation. I'm not talking about an individual carbon rotation. Individual carbon rotation is not possible in this system. Is this part clear? Now, you have to figure out in these questions where the GI is possible and where GI is not possible. Now, first question, I'll just do it for you and rest you will do it on your own. For all the questions, it's better you write it in this form. Yeah, the first, we will look for GI between carbon double bond carbon. So carbon double bond carbon system is the reference, and whatever is attached to it, using those attachments, we will actually figure out whether GI can happen in the molecule or cannot happen. So C double bond C, I have written A here, I have written B over here, and then I have written A over here and B over here. This can be one molecule, and another molecule can be, another form can be A, B, B, A. If this is the structure of one, this is one isomer. If this is the structure, this is one isomer, and this is the another structure, and this is isomer 2. So these are two different structures of A. So GI is possible over here. Why? Because we could see the difference in the arrangement. Here AA or BB is diagonally opposite to each other, and here your AA are in the same plane and BB are in the same plane. Okay. So GI is possible in this. Now, figure out on your own whether GI is possible in the other cases or not, and then I'll discuss. Stop the video, try it out, and then I'll discuss each and every case. So now, let's talk about the question number 2. In question number 2, you have C double bond C, A, B, A and D. We do not require both the groups to be same on the other carbon also. Even one set of same groups can also do. So here you can take AA as a reference. Now AA right now are in the same plane facing towards the same area, and if I change the configuration, it will be A, B, D and A. So now this A and A are not in the same area or not in the same plane, they are just opposite to each other. So this change in arrangement makes it another isomer, isomer 2. So GI is possible in this case also. Now for the third question, let's see how third question will be. So we have C double bond C, A, B, C and D. So basically all the four groups are different. Okay, so if position of one changes with respect to other, we will be able to know. So condition for your geometrical isomerism is that there should be two different groups on the carbon which it satisfies. Okay, this can have the other isomer as, let's say, if you fix one carbon and you change the another carbon. So A and D were diagonally opposite to each other. Now A and D are on the same plane, basically facing at the same area, and B and C are in the same plane. So though these isomers are not exactly cis and trans, they are called something else which we'll be talking about later on. Okay, but this kind of setup also where all the four groups are different tends to show the geometrical isomerism. It is not necessary that both the groups which each carbon has should be same. No. Not even one pair of groups should be same. It can be all four different, and still we can do the geometrical isomerism, or still the isomers what they can form can be geometrical isomers, because in geometrical isomerism we basically check the change in the relative positioning of the groups. So if the relative positioning is changing, then they can form the isomers. Okay. Now come to the fourth one. Here what you have? I think it was B. Yeah. So again it is very similar to D. In D you had A common and B and D different. Here also, oh no, this is different. In fourth, what is it? Fourth is C double bond C, A. So basically two same groups on the same carbon. This will not show your geometrical isomerism at all. Okay. Now come to the next question. Next is CH2 double bond CH2. Again, each carbon has two same groups on it. It cannot show geometrical isomerism. Look at this. This is C double bond C, H, CH3 and H. Here again, two same groups on the same carbon. Geometrical isomerism will not exist. Come to the next one. C double bond C, H, CH3 and CH3. So this says both the groups are different on each carbon, and with respect to each other their relative positioning can also be changed. Right now both the CH3s are on the same plane and hydrogens are on the same plane. If I'll do a change on it, if I let's say keep one carbon as constant and other I make a change on it, so in that case your hydrogens will come diagonally diagonally opposite to each other. Similarly, CH3 will come diagonally opposite to each other. So this kind of isomer is one isomer and the other is the second isomer. When two same groups are on the same plane are called as this isomer is called as cis, other is called as trans. Diagonally opposite to each other if the groups are, then the isomer will be called as trans. So this is just a basic information about which kind of chains can show the geometrical isomerism, or which kind of setup will be capable of showing geometrical isomerism. Here I want to bring one more important term in your notice, and that is stereocenter. Stereocenter. Now what is stereocenter? So this, let's say if I talk about the last question is CH3 CH double bond CH CH3. So carbon double bond carbon here will be called as stereocenter. Stereocenter is nothing else but that carbon or group of carbons, or the chiral carbon or carbon containing double bond, or the restricted system because of which geometrical isomerism is arising in the molecule. So it can be a pair of carbon which has a double bond, it can be pair of nitrogen which has a double bond, it can be carbon nitrogen bond, it can be chiral carbon. Chiral carbon is the carbon where all the four groups are different. So basically if I have a carbon like A, B, C and D, four different groups are attached on any carbon, such carbon is called as chiral carbon. This we have discussed in the class also, in the when I had given you a slight idea about optical isomerism. So any carbon which has four different groups attached to it are called as chiral carbons. So due to any reason, due to any group or any double bond or any restricted system, if the stereoisomerism is arising in the molecule, then it is called as stereocenter. Okay, so when I say stereoisomerism, we are not only targeting geometrical isomerism, we are also targeting the optical isomerism also, or optical isomers and geometrical isomers both. So write down the definition. Stereocenter is that restricted system, in bracket you can write down carbon double bond carbon, carbon double bond nitrogen, or nitrogen double bond nitrogen, or ring system, or chiral carbon, because of which stereoisomerism arises in the molecule. Okay. So now I'll write down few more examples over here. You will again see which all of such compounds can show the geometrical isomerism, and you will also try to point out the different stereocenters also. You can figure out how many stereocenters are present in the molecule. Okay. So I'll just quickly rub this off and write the next set of questions. Try it out on your own. So note down these questions and try them on your own. Stop the video, try them out, check whether they can show geometrical isomerism or not, and then we will discuss. So let's start discussing now. We will find out what all are the stereocenters. Stereocenters are only those centers which can actually give you the stereoisomers, or in this case we will specifically talk about geometrical isomers. So carbon double bond carbon which can give us geometrical isomers, which is capable of showing geometrical isomerism, will be considered as stereocenter. Okay. So now just look at the first compound. We have CH double bond, C double bond C, one C double bond C over here and another C double bond C over here. Let's just resolve this whole question. So it's C double bond C, I have CH3 and hydrogen. So these are two different groups on one carbon. Then I have hydrogen, and other group is nothing else but C double bond C, hydrogen, H and H. Okay. So now in this question, these two hydrogens, if they are vertically opposite to each other or if they are diagonally opposite to each other, that this configuration will be called as trans, because these are the two same groups. If they'll be together, it will be considered as cis. So we can have another form of it, that is CH3, C double bond CHH, H, hydrogen here and hydrogen here. So because these two are in the same plane, this particular carbon, if carbon double bond carbon, if I am taking in reference, this will be called as cis. This will be called as trans. So that means it is capable of showing the geometrical isomerism. What about it? It cannot show geometrical isomerism because the group present on the same on the carbon are same. So this carbon double bond carbon will not show geometrical isomerism, and hence there is only one stereo center, that is this one. Okay, so how many isomers can be formed? Only two. One is trans, another is cis. So can it show geometrical isomerism? Yes, it can show, and it has only one stereo center. Now let's talk about the second one. Now the second example, what we have, CH3 double bond CH double bond CH3. So now look here, this carbon has two different groups, yes. This carbon has two different groups, yes. So and it has, so it can show geometrical isomerism, yes. So this carbon double bond can show the geometrical isomerism because it has it is fulfilling both the conditions. One is it has a double bond, secondly it has all the groups present on each carbon are different. So these two are also different and these two are also different. So this carbon can show geometrical isomerism. Come to the next carbon double bond carbon, CH3 and hydrogen, two different groups, hydrogen and this big group, two different groups. So that means this carbon double bond carbon can also show the geometrical isomerism. So this is also capable of showing geometrical isomerism. How many stereo centers? Two stereo centers. Yes, it can show the geometrical isomerism. 2 SC, 1 SC. Come to the 10th one. Now here the problem is there is a double bond between one carbon and another, but that carbon is part of the cyclic chain. So how to solve such question? To solve such question, you have to do one thing which I'll explain you. You have to go from you have to go clockwise as well as anti-clockwise around the carbon which is carrying a double bond. So basically I will just write the respective chains over here. There is a CH2 over here, there is a CH2 over here. Okay, so we will open this cyclic chain. How will we open? I'll write it as C double bond C, CH3, hydrogen. From anti-clockwise, I'll write down the anti-clockwise arrangement. So if I'm going from here till down, what all I'm encountering? I'm encountering CH2 and carbon. So I will write it down as CH2. I encountered CH2 first, then I encountered the second CH2, and then I encountered carbon. Just again listen to it very carefully. I am going anti-clockwise and I am writing, I have opened the chain basically, and I am writing what all is attached. Okay. So it is from here, if I'm walking, I'm getting a CH2 over here, a CH2 over here, and C over here. So CH2 and C. That's how you have to open the chain. Obviously there is one extra carbon over here because I'm counting this carbon twice. Once it is once what is attached to a double bond, and once the ring completes, it comes back to the same carbon. That's completely okay. Okay, now I'll go from down to up. Basically I'll go clockwise now, and what all I'm encountering? I'm again encountering CH2 and carbon. So it will be CH2 and carbon. So aren't these two groups same? These two groups are same, right? So this cannot show the geometrical isomerism. And it has no stereo center because it cannot show geometrical isomerism. Now come to the next question. Now we'll talk about question number 11. Now again I have a cyclic system over here. I have Cl, I have double bond carbon, hydrogen and hydrogen. Do I really need to open this chain? I would open the chain when this carbon double bond carbon have two different groups. Here this carbon itself have two same groups, so this will not show the geometrical isomerism. Now come to the question number 12. I have chlorine here, double bond C, CH3 and hydrogen. So here this carbon has two different groups, yes. Now let's check this carbon which is attached to the double bond and the cyclic ring, whether it has two different groups or not. So I'll just open the chain. I can write it as CCl, Cl, CH2 and this. That's how if I'll write the chain, it will be like this. I hope you guys are understanding. I'll just write it a little more neatly. This is Cl and this is Cl, CH3 and hydrogen. Right? This is the actual molecule. Now if I'll open the chain, if I'll go anti-clockwise basically, so it will be CCl2 what I'm encountering first, then it comes CH2 and then comes carbon. If I go other way around, CH2, CCl2 and carbon. Now look at the carbon over here. It is directly attached to CCl2 right now in the upper case. In the lower case it is attached to CH2. So basically these are two different groups. We are going to consider these two as two different groups because the point of attachment is also different and the positioning of CCl2 is also different. Okay, so this is how you will get to know whether you have the same chains attached or different chain attached. This is a different chain, this is a different chain. These two groups are also different on the next carbon, hence it will show the geometrical isomerism, and this is your stereo center, one stereo center you have. Okay, now come to the question number 13. What I have? Cl, 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 double bond C, CH3 and hydrogen. Again, if I'll open it, it will be CH3 hydrogen over here, double bond C. I'll go from, I'll go anti-clockwise, so it will be CCl2, CCl2 and carbon. If from this side, if I'll go again CCl2, CCl2 and carbon. These two chains are exactly same, hence this will not show the stereoisomerism, no, not stereo, sorry, this will not show geometrical isomerism, no GI and no stereo center also. Come to this one. If I'll open this chain, it will be CH3 here, hydrogen here, it will be CCl2, CBr2 and then carbon. Here it will be CBr2, CCl2 and then carbon. These two chains are different, these two are different, hence it will show GI. It will have one stereo center. I hope you have got it. If you have any doubt, you can ask me on the WhatsApp group or you can send me a personal message. Now let's talk about the next category of GI. I mean next category as in next kind of molecules which can show you GI. So GI in ring system. So now next is GI in ring system. So to understand GI in ring system, you have to understand, let's say this, I'll just show you that explanation through a demonstration. So this is my cyclic ring. Okay, this is cyclobutane. Okay, and two carbons of cyclobutane has, I'll just draw it over here. Assume this is what I'm trying to show. This is my cyclobutane, which can be written as C, 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 C over here. And this is, let's say, has an attachment CH3 also on it. This also has a CH3 on it. And then these are CH2, these are CH2 and hydrogen and hydrogen. So what kind of arrangement is this? Is it two carbons of your ring chain or your sp3 hybridized carbons have same group? So it has two hydrogens which are same, right? Whereas two sp3 members of your ring chain, one is this, let's mark it. This is carbon number 1, this is carbon number 2, this is 3 and this is 4. So carbon 2 has two different groups attached on it. One is CH3 and another is hydrogen. And the carbon number 4 also has two groups attached on it, two different groups attached on it. One is hydrogen and another is CH3. Apart from that, if you look at the carbon, third number carbon, it has two hydrogens, two same groups attached on it. And the carbon number 1 also have two hydrogens which are same groups attached on it. We are not considering these bonds between carbon which are making rings. Okay, so we are talking about the bonds apart from the ones which have been used in forming the ring. So what kind of setup is it? Two carbons, two sp3 hybridized carbons are di-substituted. What do we mean by di-substituted? That means it has two different kind of substitutions over there, or two different groups placed on it. One is hydrogen, another is CH3. So this carbon is di-substituted by two different groups. One is CH3 group, another is hydrogen. Fourth carbon is also di-substituted by two different groups. One is hydrogen, another is CH3. First carbon has disubstitution, that means two groups are attached on it and both are hydrogen. Third carbon has also two groups attached on it and both are hydrogens. Okay, so this is what disubstitution or disubstitution with different groups means. Okay, so this is one of the necessary condition also for a ring to show GI. That means at least two sp3 hybridized members of your ring should have two different groups attached on themselves. That means the two sp3 hybridized carbons should have two different groups on each carbon. So this carbon has two different groups, hydrogen and CH3. This carbon also has two different groups, hydrogen and CH3. So now let's say this is my that cyclobutane ring which I am talking about. Now look at this. Assume this blue pen is CH3. Okay, and assume there is one more invisible hydrogen over there. Generally hydrogens you will find them invisible when they'll represent it also. They will just show the groups. Okay, so assume this is CH3 and other side definitely on the bottom over here assume this is hydrogen. Okay, so this is CH3 and this is this is CH3 and this is hydrogen. So I'm not keeping hydrogen with me, I'm just keeping CH3. We can just see the geometrical isomerism with respect to only CH3 also. So this is CH3 and other is this CH3. So both CH3s are on the same plane, facing towards the same area, basically towards the viewer. I can see it like this. This is towards the viewer. Do you understand this? Now, what can I do? If I'll revert it, if I'll rotate it, both of them will go down, that is away from the viewer. But the molecule is not changed. I have not broken any bond to convert it into this form. Okay, so no matter both of the groups are towards the viewer or both of the groups are away from the viewer, they are basically representing the same molecule with the same configuration. So if both the CH3s are towards the viewer and it is called cis, if both the CH3s are away from viewer, then also this molecule will be called as cis. Cis means both the groups should be facing in the same direction, both should be in the same plane. Okay, now if I break the bond between carbon and CH3 and I place it down, that means now one is facing towards the viewer, another is facing away from the viewer. Correct? Another is facing away from the viewer. So both were facing towards the viewer earlier. I had to literally break the bond and put it down. And now one CH3 is towards the viewer and one is away from the viewer. If I am looking from the top, this is how it is. Okay, so basically they are opposite to each other. They are diagonally opposite to each other. The diagonal passes through the center of this cyclic ring. Okay, and this configuration will be called as trans. And this configuration cannot be formed automatically. It cannot be automatic conversion, but it will require some energy to break this bond, and then that molecule will rearrange and will put the CH3s on the trans position. And that is why these two molecules are going to be two different molecules, because they have two different energies in themselves and they'll be isolable with respect to each other. So if in a mixture you have this kind of molecule and this kind of molecule, they both will have either different boiling point or different melting point or some physical property different due to this kind of arrangement, because this bond had to shift down and that required some sort of energy. That energy difference will basically make them isolable. Okay, so this is your GI in ring system. So let's see how do we represent it in 2D representation. In 2D representation, the same way how I have mentioned it over here. So CH3, let's write it this way. So this is my cyclobutane and this is my CH3. So I have two attachments over here, CH3 here and CH3 here. Okay, just by looking at it, you won't know which isomer it is. You will have to very precisely mention the arrangement. Now there is a structure called as dash and wedge structure. Dash and wedge structure. What does it mean? Dash and wedge structure means we put dash 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 in those areas or in those bonds which are away from the viewer. Okay, and we put a wedge, a solid wedge like this. This is a bond, this is a solid bond which represents that this bond, this group which is attached to this bond is towards the viewer. So this is called dash and this is called wedge. So now as I had shown the placement of CH3 towards the viewer and hydrogen away, this CH3, this CH3 was facing towards the viewer, right? So the another hydrogen which is present is going to be away from the viewer. So that kind of arrangement can be shown on 2D geometry is like this. So this, if I put it as a solid bond CH3, this means this is towards the viewer, and I can place a dashed bond next to it, which will show that hydrogen is down, that is away from the viewer. Again here, if this is a wedge bond of CH3 and there is a dash bond of hydrogen, that means both of the CH3s are facing towards the viewer. That means the configuration right now is cis. Okay, I had already shown you this. Cis mein both the CH3s will be facing towards the viewer or facing away from the viewer, but whatever the arrangement is, it should be same for both of the groups. Okay, even if I form this kind of molecule, that is dashed for CH3 over here and dashed for CH3 over here, and wedge for hydrogen over here and wedge for hydrogen over here, this arrangement will also be called as cis. Okay, now what is trans in this case? One is dash, one group is dash. Here you have CH3 as wedged and hydrogen as dashed, whereas here your CH3 is dashed and your hydrogen is wedged. That means CH3 here is towards the viewer and CH3 here is away from the viewer. In this case, this will be called as trans. So that's how we represent the geometrical isomers in the cyclic ring. So what is the mandatory condition? Mandatory condition is at least 2 carbons of your cyclic ring must have 2 different groups attached on them. And that carbon should be sp3 hybridized carbon, no sp2, no sp. Okay. Now let's take some examples and see which all compounds can show GI, which all cannot show GI, and how many stereo centers are present in the molecules. Now in these questions, find out which all compounds can show you GI with respect to double bond or with respect to ring or both. The overall idea is the molecule should be capable of doing GI, irrespective of it is because of double bond, or it is because of ring system or whatever. Okay. So try it out and then I'll discuss the solution. Let's talk about the first compound. So first compound has, first of all we will see there are 2 things in this molecule. One is carbon double bond carbon and another is the ring system. So carbon double bond carbon, we will, and there is a ring here, a carbon and a ring. For that we generally check the open chain carbon has 2 different groups or not. So there are no 2 different groups on this carbon. So hence no GI due to double bond. Okay, so this part of the molecule cannot show GI. Okay, so now we will see whether ring individually can show GI or not. So what all conditions are there for a ring to show GI? 2 sp3 members should be disubstituted or should have 2 groups on them, should have two different groups on them. So let's see whether it fulfills this condition on, we are talking about this cyclic ring only. So this carbon is sp3, this carbon is sp3 and this carbon sp3. 2 carbons over here. I'll just write it separately over here. So this is how the system is. The rest of the attached system is not participating in GI. So this is C double bond. So there is only single carbon over here. Okay, no CH. Here I have carbon with hydrogen and Cl, and again carbon with hydrogen and Cl. So this carbon, so basically this carbon has 2 groups, 1 chlorine, 1 hydrogen. Again this carbon has 2 groups, 1 hydrogen and 1 chlorine. So basically fulfilling the condition what is required to show GI for a ring system. Okay, so can it show the GI? Yes, it can. How will it show? Just look at this question. So in this case, in one case Cl may be towards the viewer, okay, and rest of the system will remain as it is. And in the other case, the Cl may be, in other case, this for one carbon Cl may be is towards the viewer, that is wedge bond, and for other it is away from the viewer, and rest of the system remains same. So these will be two isomers formed by this molecule. So Gi due to ring, yes. Gi due to double bond, no. Stereo center, only one. Which is the stereo center over here? The ring system. Okay. Now let's talk about the second compound. Now let's talk about the second compound. Second compound is cyclic ring with two chlorines. Is this an sp3 atom? Is this an sp3 atom? Both are sp3. What all the attachments are over here? Hydrogen, hydrogen, chlorine and chlorine. On rest of the places there is hydrogen, 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 hydrogen. So only these two are the carbons where two different substitutions are there. So can it show Gi? Yes, it can show Gi. How? One compound will be with both the chlorines towards the viewer or away from the viewer, either way it can be. Okay, so do not get confused that it is always towards the viewer. Both can be away from the viewer also. Okay, and this is one away, one towards. So this is how it will show Gi. Next, let's talk about the third question. In third, what is there on this carbon? Two hydrogens. What is there on this carbon? One hydrogen. What is there on this carbon? Only bromine, no hydrogen. What is there on this carbon? Bromine and hydrogen. Can this ring give you the, can this ring show Gi? No. Why it cannot? Because here the carbon where bromine is attached or any other carbon apart from this and this sp3 carbon has two hydrogens. This sp3 carbon has one bromine, one hydrogen, but rest of the two carbons are sp2. And what is the mandatory condition? At least two sp3 carbons should have disubstitution. So this will not show Gi, no Gi. Okay. Now come to the next one. In this, what all we have? Two hydrogens here. Here one CH3, one hydrogen. Here two CH3s. And here two hydrogens. Can this compound show Gi? No. Two same groups here, two same groups here, two same groups here. It will not show Gi. Okay. Come to this. Now in this case, we have hydrogen, hydrogen, two hydrogens here and two hydrogens here. So these two carbons cannot show Gi of the ring, but this and this carbon can. So there are two sp3 carbons with two different substitution. So in this case, once this CH3 will be, both the CH3s will be towards the viewer. You need not to represent hydrogen at all. Only representation of CH3 would be enough. And in the other case, that is trans, one will be towards the viewer and other will be away from the viewer. Okay. Come to the sixth one. So condition for any ring to show Gi is that at least two sp3 carbons should have disubstitution. Here we have three carbons which have disubstitution. H, H, H. Can this show Gi? Yes. How? Let's see. Now this is always going to be with respect to each other. Okay. Let's say all the three are facing towards the viewer. This will be called as cis isomerism. All the three are away from the viewer. It will be also called cis. Now conditions where two are facing towards the viewer and one is away from the viewer. Okay. So in this case, what will happen? We will ignore the fact that there are two which are facing towards the viewer. Basically, we will consider two chlorines with respect to one chlorine. So here, this Cl is in trans with respect to both of the chlorines. So this kind of positioning will be called as trans. Okay. It can be this way also, where two chlorines are away from the viewer and one is towards the viewer. The whole idea is that there should be opposite configuration. Here two chlorines with respect to one chlorine are in the opposite configuration. This is again called as trans. So these all, when all the three will be facing in the same direction, or you can say will be in the same plane, they'll be called as cis. Even if one has a different configuration, it will be called as trans. So your sixth one will also show Gi. Okay. Now come to the seventh one. Now seventh one, again let's check. This is a 5-membered ring and we will see which all carbons have different groups attached to it. So this is your sp3 hybridized carbon, but both the groups attached over here is same, so it will not show Gi. Okay. Now here you have CH3 and hydrogen. Here you have two chlorines, it will not show Gi. Here you have two bromines, it will not show Gi. Okay, same group is present. Here you have CH3, here you have CHO and hydrogen. So with respect to this carbon, I'll just mark carbon 1, 2, 3, 4 and 5. So carbon number 2 and 5 with respect to each other will show Gi. If both the hydrogens are away from the viewer or towards the viewer, the configuration will be called as cis. If they are in opposite configurations, if one is towards the viewer, one is away from the viewer, then the configuration will be called as trans. Okay, so this will also show Gi, and Gi will be shown by second carbon and the fifth carbon of the ring. Okay, in the next class we will understand the Gi in a ring with a double bond. So if there is a double bond inside the ring, how that can show Gi, that we will understand. Right now I'll give you some questions, you will try it out on your own at your home. I'll share the answers saying that whether Gi is possible for a particular compound or not. If your answer doesn't match with that, you can ask me it as a doubt. So solve these questions, try out on your own, which will all show Gi, which all will not. And then if you have any doubt in any of these, you can ask me in the doubt group.